Welcome, everyone. It's a great pleasure to introduce Dr. Ismail Bustany for today's special edition of the TILOS seminar. Ismail is a fellow at AMD, and he works on physical design, implementation, and machine learning for CAD. He's been on numerous program committees. He was the general chair of the International Symposium on Physical Design several years ago, and he's well known for defining, organizing, running a number of very influential contests in the physical design domain. His research interests include physical design, computationally efficient optimization algorithms, MLCAD, sparse matrix computations and acceleration, and partitioning algorithms. His bachelor's is from UC San Diego. We actually met 37 years ago, or some absurdly long number of years ago. And his master's and PhD are in EECS from UC Berkeley. So please take it away, Ismail.
Thank you, Professor Khan, very much for this great introduction. And Professor Khan was my TA when I was at UCSD. Very fond memories. And thank you so much again for inviting me to give this talk to your esteemed audience. Hopefully I'll do some justice in conveying some ideas we have about ML for FPGA. Part of my talk may be boring to some of you, but I try to make it simple to understand for folks who don't have background in physical design or FPGAs. And also maybe I will give some backgrounds on ML. So I apologize if it's going to be, some sections may be boring for some of you. But I hope I will add some insights or some additional knowledge that you didn't have in some areas. So the title of my talk is, sorry, I'm going to start a timer here. It's the FPGA physical design flow through the eyes of ML. And let me explain the outline. So I'm going to give a taxonomy of ML and the PD flow. PD stands for physical design. And I'm going to try to tell you why ML is compelling in particular for the FPGA physical design flow, more so than in ASICs. And then I'm going to show some snapshots of ML and parameter optimizations examples that we do inside AMD. And the kind of towards the end of my talk, it'll be more kind of a tutorial really of where I think we should be heading in using ML and deploying ML for solving this problem. And I think a lot of you in the field have already done that. So, but I'm just going to be paraphrasing what you've done there. And then instead of a conclusion, I like to give practical learnings from deploying MLCAD in the field. And so hopefully I'll share that with you. All right, so taxonomy of ML and physical design flow. Before I start that, so just to even the ground field, so maybe some of you haven't seen an FPGA, but this is how an FPGA looks like. The one on the left is actually one of our biggest FPGAs. It's a DU19P. The reason it's this big, because we care about capacity. It's used for emulation flows. Obviously, we have much smaller ones, but this is one of the biggest ones we have. And the one on the right is an Elvia board. And this is for high performance computation. And it's kind of our latest 7 nanometer technology. These days, actually, we talk about FPGAs, and a lot of you know this, Professor Andrew Khan, C.K. Cheng, Professor David Pan, in the audience. It's not just an FPGA, really, it's a system on a chip, right? So we have a TensorFlow kind of array in these boards now. There's a resident CPU, there's a microcontroller, a lot of small other chips in there that comprise that SoC. Today's talk is mostly about the FPGA itself, but the problem that we are solving now in AMD and in Xilinx before wasn't just restricted to an FPGA, it's really restricted to the ecosystem of an FPGA, which involves those other peripherals and computational units. And the problems there are also very, very intriguing. Maybe we can avail them in a different talk in the future, or somebody else can do that. Okay, so for an FPGA, unlike ASIC, I just want to show you how the placement grid looks like and what's inside of it. So most of FPGAs, this is kind of a one of the older technologies we have. They are made of, they're pre-made templates, and they have clock regions. So these are clock regions. And then the logic basically is collimated. So you have these columns of logic that we call them configurable logic blocks. And each configurable logic block houses lots and flip-flops. And then also along with those CLBs, we have columns of memory, mostly DRAMs and URAMs, and then columns of DSPs. And then intermingled in between, there are columns of IO. Sometimes the IO is in the middle of the device itself or on the periphery. And the cell library is also different than ASIC. It's basically lots, flip-flops, carries, DSPs, BRAMs, and URAMs. The layout grid is also very interesting. It's already pre-laid out for you. There's no like layers and what we have in typical ASIC. Normally, we can think of it as a device model. You normally think of it in the 2D space. It's comprised of a mesh. And the mesh, you can see, there's an artist rendition here. The CLBs are communicating with this interconnect routing grid through some wires. The CLBs are highlighted in yellow. And then there is some like IO columns in there as well. But what's interesting about this interconnect routing grid, it has this, it's a switch matrix mesh. So each one of those switches has in it programmable, what we call programmable interconnect points, which we call pips. And then these pips connect basically to some wires. And these wires, again, they're not layers. You think of them as in the 2D plane. And we have short and long wires. So like on the right side, this is one of those switches, switch matrices. Incoming to it, you see a pip, like this point. And outgoing, there's another pip. And from this pip, you see there's like a red wire. That's the wire segment. And like I said, these wire segments vary in length. Short wire, single, double, quad. When I say single, double, quad, what I mean is how many CLB columns they traverse, okay? So think of our wiring problem more of it's like a grid graph representation with not continuous length wires, they are discrete length segment wire. And when you have a routing path, the way we designate that, we basically connect these pips. So if these pips are on, switched on, then the wire segments coming from the left of the switch to the right will be connected. And that's basically how you do routing. You turn on these pips. Okay. So how about what does the physical design flow look like? So here I'm going to just quickly go over the differences between the physical design flow and FPGAs versus ASICs. So in the ASIC flow, Professor Khan actually and David Pan have written a book on this, right? It's rather complex. You know, there's a synthesis step, there's a placement step right here. There's a clock tree building step. And then after clock tree building, we route the design, and then we do what we call post routing or post CTS optimization to get some timing closure. Then we do verification, timing sign off, and then we print a GDS layout. And typically the time budget for an ASIC flow, a physical design flow, ideally we aim for it to be hours, but in all practical purposes, it really takes days, sometimes weeks to converge. For the FPGA physical design flow, it mirrors its cousin, its sibling in the ASIC flow, but you'll see there's some additional categories in here. For instance, in FPGA flow, we do have synthesis, we do have placement, we have routing. We don't have timing sign-off and post-routing optimization. Everything is done for us from the get-go. So the clock, actually, there's no clock tree synthesis. It's already done. So what we do, since the clock is already in the FPGA device, we need to generate what we call clock region constraints. And I'll go a little bit over those. And then also, see, like this step is missing, clock tree synthesis. You already have a clock. And then instead of a GDS layout, we generate a bitmap. And the bitmap, if you have a device, you don't have to go to manufacture the ASIC or the FPGA. You have an FPGA resident in-house. You just turn on the, you write the bitmap, and then you have your hardware delivered to you right on the spot. A typical design flow for FPGA is much shorter than your typical ASIC flow. So in our case, it takes hours, few hours. We would like it to be minutes for simple designs. So even though it's a smaller kind of physical design flow, the time budget is much more strict than ASICs. You will ask, why would it be much more strict? Because we service a lot of customers from different fields, like especially in the past few years, we service AI customers. And if you're an AI person designing, if you want to accelerate a DNN or CNN, you're not used to long compilation times. You write your code in Python, and you're not an RTL engineer. You'd like some kind of translation to represent some kind of representative language that will take your Python code and then deliver a bitmap to an FPGA. So for the Pythoners of the world, and they are growing very, very fast as a customer base for us, we would like that flow to be much more seamless for them, much like really the budget for runtime, it's very, very, very sharp. And it has a lot of implications on our physical design flow algorithms. So we need an order of magnitude speed up, or sometimes 2 orders of magnitude speed up on that front. So on the left side, I just highlighted the differences, like in synthesis, the library for FPGA is composed of lots, flip-flops, and carries, and all those BRAMs and DSPs. They're not like simple gates. The memory blocks in the synthesis are inferred rather than explicitly assigned as in ASICs. And there are some implications for technology mapping. Once you've done that, the optimization also has some special recipes that we follow. Mostly, it's kind of bottom-up rather than top-down. And on the placement side, most of the FPGAs, they are not single die. They are mostly multi-die. So from the get-go, our physical design flow has to be multi-die aware. So partitioning is a key component in a physical design flow in FPGA. There's no power mesh generation, obviously, there, because it's already made for you. I/O and clocking is different. Like I mentioned, there is a pre-built clock tree. There's no clock tree synthesis. Slew fixing is much easier. But there's one restriction. We have a limitation of the number of clocks you have in a particular region, depending on the technology. But they are like in the 20s or 30s clocks you can have in a particular region. And this has implication on the logic placement, because then you have these control sets. And when you place your logic elements, they have to obey those clock constraints. Okay. Global placement is more discrete. Again, we have these collimated site grid. So it's not continuously kind of placed. You have to place them in these designated columns. And you have to obey clock region constraints. Detail placement, in a sense, it's easier. There are no design rules, mask rules, or proximity rules. But it's mostly legalization with respect to clock region constraints and basically putting them on the columns. So it's a little bit easier in that sense. Routing, it's not 3D. Our device models for routing are 2D. But they are segmented wires, so you have to take that into consideration. And again, there's no DRC checking. Everything has been done for you from the get-go. It's rather than a DRC rule checking, you really have a state machine, you have a pip state transition rule machine that you have to follow. That's a big difference there. Timing, it's a buffer delayed model. It's not RC networks, so it's a bit easier. In the optimization, for instance, there's no gate sizing or buffer insertion. We do a smaller set of tools to optimize for timing closure. Mostly, I would say we do remapping, really, mostly for that, logic remapping, but not beyond that. One interesting different flavor with FPGA, this physical design flow, is we have what's called design flows. So remember, we service a lot of customers. So we have emulation customers, we have prototyping customers, we have AI customers, high performance in the data center customers. So there's good ROI for us to specialize the flow to the application, to the domain. So the emulation domain, we have a special flow for that. HPC, we have a special flow. Prototyping of chips, we have a special flow, and so on and so forth. So it does make sense for us to specialize the flow there. In ASIC, I think you have to be a generic tool servicing everybody and everything. For us, we know the customer base and we have a device family that's living, so we can afford to specialize it. And that's the key difference, actually. And it will play into the taxonomy when I get there. So if I look at the research in ML in the PD flow, this is kind of what I think of it as the taxonomy is. We use ML in modeling, in parameter optimization, and more recently in end-to-end optimization. So in modeling, for instance, a lot of work, Professor David Pan has a lot of work on this, obviously. Professor C.K. Cheng also has with the new version of Replace and Dreamplace. So there's, you do congestion map modeling, or like, for instance, routing effort prediction. Professor Andrew Kahn has worked on this problem many, many times, obviously. And then also time delay estimation. That's very key for us. So the nice thing you'll see as I go through my presentation, a lot of these, when you come to the FPGA world, the device models are very well done, and we know them. So coming up with these models is rather much easier and transparent than doing it for ASICs because it's a one-off. Parameter optimization examples, for instance, in synthesis, we have a transform predictor for runtime speedup. We can work on, a lot of work has been done on placer parameter optimizations to improve QOR, quality of results. Global router also, we have parameter optimization to improve runtime. There's recommender systems for physical design for timing closure, like what kind of recipes used for physical design. There's a lot of feature identification and parameter selection maybe for graph partitioning. This is kind of nascent work. I don't have examples for it yet. I know Professor Andrew Kahn is working on that, so hopefully some things will come. I know some things will come out of it. And then end-to-end optimization, mostly it's the concept of learning to optimize. And this is what I think Professor Jitendra Malik and his student Kaylee, who's also a professor now, coined that term 2016, 2017, learning to optimize. And I know a lot of in this the audience here are researchers in this area. So the applications for L2O span from floor planning to standard cell placement to routing to partitioning. The ones on the top, the modeling and parameter optimization, they are mostly, I would say, use supervised learning models. So they are very well understood tool sets. The deployment in the field is very clear for us. I would say relatively clear. Mostly classification, regression type supervised learning. There is some nascent RL-based work in parameter optimization. I don't think it's, and actually not only that, also in delay estimation, some work, like Synopsys has done some work in that, and it's in the field already. The one thing that we care about as from the commercial and industrial side is the life cycle management, the life cycle management of the model. Like, when do you update the model? When do you know the accuracy is bad? What's versioning like? So these things we have to take care of. On the learning to optimize front, I would say, obviously, this is one that learning data is, the label data is sparse. It's not very much data you have. But when you do a placement, you cannot do millions of placements. You typically have thousands of placements. So you have sparse data. And then also these tools currently are very expensive to train, but they have very highly promising QOR. So we're looking into them very closely. Okay, so let me just quickly say why it's compelling to do ML for FPGA more so than ASIC. I mean, I came from the ASIC world, but when I joined the FPGA world, it was an eye-opener for me. So aside from the obvious reasons why you do ML for physical design, it's a complex problem. It's multidimensional, non-convex, NP hard. It works best on large data because we have large data sets. And we have big models, like regression and classification problem with a lot of data. And we have, like I said, small data, like sparse data problem, like placement and routing. And obviously, ML can be very good for solving these problems. But this statement would apply both equally to ASICs and FPGAs. And so what's special about FPGAs? In FPGAs, we have device families that are templatized, and these are programmable. So there is a high ROI. We have a very solid understanding of the models, the device models. We actually own it. It's in-house. So querying the physical design flow for the models of the device, it's very transparent for us. So we have full view of the models. So that's a very powerful thing. So it's not only is transparent, but also if you design a solution for one FPGA, it's not one FPGA, it's an FPGA family. And these families have a life cycle of about 10 years or more. So the ROI for your ML investment is very high. And we have vast amount of device and design data. We have, like I said, many different type of applications in machine learning and emulation, auto, DSPs, wireless, aerospace and defense, data center, database applications, financial applications. So there's no shortage of data from the field. Like we have a lot of data. So that affords us to develop more robust ML models. And then at the same time, because we service a lot of customers, you can do design specific, you can do domain specific ML. Like I said, we have design flow specific ML flows, physical design flows. You can use that to your advantage. It'd be the same kind of problem that you see, and you can use that to do ML solutions at scale for these particular domains, which is a luxury I don't think we've had in the ASIC. And then it's a one full, it's basically with the FPGA physical design flow, we don't have point tools. We have the whole flow we own. That's really good. So we can harvest data, instrument, plug and play tools inside of this chain, this tool chain at will, basically. Okay, so that's very powerful. In 2021, we released our Vivado ML. There's a video, but I don't think I will play it. It's a market. I mean, it's a nice video, but you can go and if you go on our webpage, you'll see it. It will advertise what we do. But let me tell you what's inside that tool. There's a modeling and optimization frameworks through ML. So let me quickly give you a snapshot of what's in there. And there's more that's coming, but I'll just tell you what was released. So we have a delay estimator. We have a routing congestion estimator. We have a runtime prediction estimator for emulation designs, basically telling us which designs will take longer. So we can use we can a priori prepare more compute resources for those designs or not. And we have an IP resource estimation. So let me quickly tell you what these are. So the delay estimation, it's basically when you have a design that's not routed, you want to estimate the delay because that helps you in timing closure. And this is kind of what we get. We know the device model very well. And like I said, it's collimated. So the trick here, when you estimate your delay, you need to know when you go from a source CLB to a target CLB, a logic element to another logic element, you're going to cross through tiles, through those columns. And as you cross through those columns, some of these columns are CLBs, some of them are memory units, some of them are DSPs, some of them are IOs. So they have different time delays. But that time delay is actually characterized. We have the device models that characterize those delays very, very accurately. So we can use that to our advantage. So if I have a gate placed some distance away from another gate, I can do regression on it and find out all these crossings, accumulate the delay across those columns, and then come up with very rather accurate models. So what I'm showing you here is on the left side, we used to do empirical models. So we used to have somebody come and sit for every generation of an FPGA device. By the way, we have a lot of generations. Like for a device family, you may have, for a given device family, you may have like 30 subgenerations of it. So imagine sitting down, trying to come up with a delay estimation model for 30 device models for each generation, which was very time consuming. And the results you get here, if I show you on the left side, this is the baseline, what you compute from the router, the actual delay, versus the estimated delay with a hand-cooked model that took literally months to develop. The accuracy is not very good. It looks like a baseball club. With ML, it looks like a lightsaber initially. So that was a very big finding for us, that we can actually do really accurate models with ML. And it's cheap. It doesn't, we have the models now. It takes a few hours to run them and we're done. And these are kind of the accuracies you see, like it went up from 68% to 97% at the 5% error point. Okay. Congestion estimation is very valuable when you do placement. So again, we can do congestion estimation. I'm not going to go into the details. A lot of you have done this. I know Professor Andrew Khan, Professor David Pan have done this with DreamPlace. But basically, this is what you get. I mean, if you have, you can think of the congestion map as a stack of images, and you can have a decoder encoder, for instance, to come up with an image in the end, which is your congestion map. And again, with the hand-cooked models, what I'm showing here, like if this is an estimated model, this is the actual model, this is the error between the two images. This is the kind of error you get. You want it to be white screen, and you don't. With ML, you're approaching a white screen, which is nice. Okay. We also have compile time prediction, like I mentioned. So we have a flow where we service emulation customers, and these are very, like I showed you in the beginning of my talk, this big BU19P device. That's what our customers use for emulation. Many of them, a farm of those devices, and it takes many hours to run those designs. So some of those designs don't take many hours; they take a few hours. So it's important for us to be stingy with compute resources. So what we did there, we basically did a classifier that from the netlist identify this netlist will take longer runtime or not long runtime, and we bucketize them. And that was very profitable for our customers, because now they don't have to devote as much resources for some of those netlists a priori. IP resource estimation is another thing. Is when you before trying to come up with an implementation, you want to know how much IPs you will need to target a device. So if you have 10 IPs, I mean, how much logic you want to expend on this IP. Because that will help you in determining which FPGA family to use. We used to have a very cumbersome process of doing this before, or actually it depends on the knowledge of the user. Now with ML, we can automate this process very quickly. So it saves from days, literally, basically minutes or hours. Parameter optimization, we have a recommender system for physical design flow. We have a synthesis Boolean optimization strategy, again, to classify which kernels to use. We have a placement directive recommender, kind of algorithmic selector, ML multi-classifier in there. We have a router, again, parameter selector. And very quickly, I'll go through them. Like if you do the strategy selection, this is something in FPGAs. We have about 60 recipes when you go through our flow that we give to our customers. And it was really cumbersome to know for a given design, which of those recipes I should use to time close my design. And what this work did, we basically did a regression on it. And then from netlist and placement features, we come up with the best top 3 recipes that we recommend to the user. And again, that saved a lot of time for users, from days to hours. And not only that, it gives them very quick access to high quality recipes. Okay, another one is basically synthesis Boolean optimization, and that's basically we train it to see which, based on the sub-netlist characterization, what kernels we should use in opt in synthesis. And that increased, basically gave us about 30% speed up. This is a placement directives classifier, gave us about 2% POR improvement. You think 2% is not a lot, it's actually a lot on average, because that's a geometric mean. So actually that's a good result. Same thing with the router. We also have a regressor that goes and identifies some properties and features of the netlist, and then eventually we got about 25% speed up. That's a big thing, because the routing in FPGAs is, especially for emulation designs, is where the runtime is. So 25% translates a lot. Now let me segue to kind of the more preaching part of my talk. And For some of you, this will be kind of boring because you are the researchers in this field, especially in the foundation segment of TILOS. So just bear with me in this portion. So this is kind of what I think of optimization classically versus L2O. Basically, the approach in classic optimization is founded in real rigor and real analysis, control theory, Lyapunov stability, right? And the tools we use there are tailored more toward problem specific. Like we have an LP, I have a QP, you have a matrix inequality, and so on and so forth. And we also subclassify them as sparse or dense. And then we design algorithms for them, like an SOCP and so on and so forth. With L2O methods, we don't really have that designation. It learns from, it improves learning from, there's no tailored algorithms. It's mostly, you run it on sample problems and its behavior improves on the sample problems. And training is offline and time consuming and performance improves with data. The building blocks for us in classic optimization are the classic, algorithms, Newton's method, simplex, conjugate gradients, Lagrangian duality, etc. Nesterov momentum methods. In L2O, it's Markov decision process, RL, neural net, scans, GNNs, GCNs, and classical optimization methods, right? Because we always go back when we do training to that. It's a virtuous cycle. Classic optimization, it's geared in theory. We have rigorous proofs. L2O, it's more empirical, lacking proof there. Still, it's a nascent technology. Performance-wise, in convex optimization, we have provable, we can find the global minimum. For non-convex problems, we can find local minima with classic approaches. L2Os can have an advantage in both of those areas. In convex optimization problems, sometimes they can, if you have a similar type of distribution of problems that you are training on, it's been shown with L2O that you can have faster convergence. And for non-convex problems, they have the potential to give you better solutions. And this is kind of what I'm saying, why we need to go there. Basically, because with L2O, unlike with classical, if you train your optimizer on a specific type of problem where the distribution of data is similar, and that's termed as similar task distribution, then your L2O optimizer will fit to that distribution and sort of will get these kind of shortcuts, which the classical approach does not find. And then it can converge faster. And the interesting tidbit here is, the reason I'm mentioning this, because in FPGAs, we have these design flows which have similar task distribution. So I think L2O may be a good application for, in particular for the design flows, like the emulation flow, etc., and the AI flow, etc. Okay. These are some examples of where L2O works. It has been shown to work, like in Lasso, in neural net training. There are some examples I'll show later on. There's a very nice survey in 2021. I'm giving a link for it below. I think it's really worth reading, where they show a lot of good examples where L2O is beating convex optimization in runtime, in rate of convergence. Okay, so what is this L2O paradigm for the researchers in the audience who haven't seen it probably, but I know most of you have. And basically, the way Jitendra Malik and Kaylee describe it, which I like the description. They took an optimization algorithm, so 3 steps. It's a classic continuous optimization algorithm. What's in a classic optimization algorithm? A continuous one. You have the data, the initial points. You have to complete a search direction, step length, update step, and do a test. If the test converges, you stop. Otherwise, repeat to step number 1. So the model for L2O would be something like this. Instead of compute the search direction, you learn the search direction. And instead of compute the step length, you learn the step length. So our learner will be trained to learn the step length and learn a policy for the search direction. So notice I mentioned the word policy because we typically use, we use RL for L2O. And I'll tell you why. I'll try to tell you why we use RL for that. So just a quick background for the uninitiated, and RL, basically, there's a state, set of states, set of actions. There's a probability density function for moving from one state to the other. And there's an initial one, and there's a state transition probability density function. There's a cost or a reward, depending on which camp of the world you are. And then there's a time horizon for running it, for running this training. And then there's a policy. And basically the policy, the job of the policy is to minimize an objective or maximize a reward over time. So the expected reward over time, and this is what we call the policy. The very interesting assumption about RL is it doesn't assume, by construction, it has no knowledge of the transition probability. It discovers that as it goes, as it trains. And it turns out, and this is according to the research work that Malik and Kaylee have done, and many of you in the audience have done, it turns out to be a very crucial assumption that RL has. It's a very nice feature in RL that doesn't assume knowledge of that transition probability density function. And you'll see in a second why. But before I tell you why, this is how you map your continuous optimization algorithm into an RL-based algorithm. So you learn the step length and the search direction by doing a policy. Actually, it becomes a dual policy here, one for the value for the step length and one for the gradient field. So it's a kind of dual policy you have to learn. Your action is basically designated as the line search times the step length times the line search times the gradient, the search direction. And then your state is basically the collection of the iterates, the function values, and the gradients throughout the iteration. And the cost function is just your objective. So this is that's how they actually map it into an L2O. It's a very nice, elegant mapping, I think. All right. And now why do we use RL rather than have that policy learned through supervised learning? The problem with supervised learning is there are two assumptions. First of all, is at every time step in the learning process, this process is IID. And then also the dependence on future observations on the current observation is kind of known with supervised learning. And both of those assumptions are not correct, actually, because in our case in optimization, the step length, when you vary the choice of step length really will impact the future choice of the search direction. And also how it's impacted is not known. All right. L2O, because RL does not have knowledge of that probability distribution, probability density function for the transition density function, it's kind of immune from that. So it doesn't tend to overfit to the geometry of the objective function that we are trying to minimize. So if you train it for one objective function, it actually can probably work for other objective functions. And that's really the key property, that while supervised learning tends to have a bias towards the data that's overfit, the kind of the geometry of the objective function is trying to fit to, RL doesn't have that bias, or at least it suffers less from that bias. Okay. So the implication of it is, and actually there's a very nice work that compares the two. There was a paper done on training an L2O with a supervised learning model. What happens with the supervised learning model is it has a policy for the alpha and a policy for H. The problem is it computes, this was a problem only for alpha, not for H. It computes an alpha, a step length, and then it sees a gradient, but the gradient, it was kind of unexpectedly, it has not the same properties it was trained on from the previous objectives. So it will mispredict the step length. And that misprediction will make it not quite a descent direction. So it may veer off of the descent. Eventually, the next step length will see a different gradient, which is not quite what it was expecting. And eventually that process can diverge. And that's the problem with supervised learning. And there's a very nice work on that. I think I'm not showing the reference. Okay, while with RL, like I mentioned, it doesn't quite suffer from that. So let's see if it really works in practice. So there's, again, from Professor Malik and Kaylee, they have this nice work where they developed an L2O optimizer. And the job of that optimizer was to train a neural net. So instead of using Adam's method or you name it, whatever tools sets we have in TensorFlow, like SGD and stuff, can we use an L2O to put an L2O in the tool set of TensorFlow to optimize, to train in a CNN? So that's what they did. They took a CNN, a simple one. It's a two-layer, and actually a neural net in this case, but it's a CNN. It has 48 inputs and 10 outputs, and they trained on MNIST image data set. And then to test the optimizer to see how well this optimizer will work to train other neural nets, they took 3 different data sets. Some of them were grayscale, not colored, and some of them they have colors, and they're kind of much bigger data sets, like with 10 categories and 100 categories. So they're kind of different animals than the ones they actually trained the optimizer on. So did it work? And it was very interesting. So this graph right here, this plot, the red one, is the L2O optimizer. So what they did is they took a same structure neural net, identical to the one they trained on, and it actually worked very well. It worked decently well. In fact, most of them worked decently well. The one that didn't work well was this one, which was an LBFGS, but I don't think we use much LBFGS in training neural nets these days, right? We use SGD and the likes. But for the most part, everything worked decently well. Then what they did, they changed the architecture. So while there's another one here, there's another one that in blue, actually, an L2O optimizer. This is the one I was mentioning earlier on, that used supervised learning to train it, to come up with the policy. Once you change the underlying structure of the neural net that you are training, the structure of your objective function geometry changed. So you can see what happened there. It kind of starts to diverge. While the L2 optimizer, which with RL, it kind of starts diverging, but then it recovers and it converges. And actually, for those 3 different data sets, it converged throughout. And then what they did, they tried a longer time horizon. And again, the L2O RL-based one converges while the other one is not stable. And the last thing they did was they added noise. So instead of having their batches for the stochastic gradient like 200, they make it like, I think it was like 10. So really, really very inaccurate stochastic gradients. And again, you'll see a lot of struggle, but eventually it converges, the L2O. So it seems like L2O in that framework with RL really is, I think it has a lot of potential. This work actually was very inspiring to me when I read it. And that's why I feel strongly about it. And I think many of you in the audience probably share that view. A lot of nascent work has been in L2O. I just list really a handful of them. Professor Pan, Professor Andrew Kahn have, in the audience with CK Cheng, have a lot of work in this field. And we are seeing a lot of work happening in this area. Very nascent in parameter optimization and standard cell placement, macro placement, core device placement, like the big chips, not at the lower scale, right? Like what Cerebrus is doing, ASIC routing, and so on and so forth. A lot of great works. I'll just give a very quick sampling. There's the work from Google, Azalea, Mir Hosseini, and Anna Gould's macro placement work that use an RL. Basically, they use this 2 policy network for one of them for the objective function, which is wire length, and the other one is for the kind of the gradient, really, of how to move the macro blocks. So this is very interesting work. I'm not going to go over the details, unfortunately, just for the interest of time. But the results were very impressive there. It beats a human-trained floor planner. So that this work was based it was inspired by their AlphaGo Zero work. And this work actually was very interesting and actually inspired a lot of us in the field to kind of emulate it and start working in that direction. This is kind of shows you, like, if you, what this is showing you, if you start training with transfer learning or without transfer learning. So one goal is for us, when we do these RLs, when you deploy them in the field, you may need to train them. And training them on the field really is time consuming. And if you do it from scratch versus not from scratch, so they're showing here, let me show you kind of If you do it from scratch, it may take 24 or 40 hours to train. But if you have it, if you can just train it with, take a trained network and just train it on the go, it may take a couple of hours. So that's more tenable for floor planning. For standard cell placement, 2 hours of training may not be quite tenable. So we need something much faster. Okay, but I know they've actually improved the speed since they published this work. So I don't know how far they've gotten it through. Another very nice work is from Professor Sang-Hyu Lim from Georgia Tech. Really, really nice work. Again, they use a two-policy network, and what they do, they take a placer and they optimize the parameter for the placer. You'll notice that the feature set that they get here are netlist-based and placement-based. But the interesting about those features, they use things like Fiedler vector, coloring metric, Rent's exponent. I think they probably had that in there as well, spectral radius. So they use a GNN in there, and the feature set they do some graph embedding. So a lot of those tool sets that I think in the foundations charter, if we can speed up those elemental toolkits, tool sets that do some kind of learnings on hypergraphs and graphs, it will be very useful for us to deploy them as features in our machine learning when we use RL. This work is really, I think not only me, many folks are impressed by this work. The results are really good. And the interesting about them is with this parameter optimization, it's a one shot. So they train it, and because RL is robust, it has this robust feature. And it's really robust. I mean, it's a one-shot parameter optimization. So you give it a design unseen netlist, and with one shot, it can go and gives you the parameters values, and it actually beats a humanly trained model placer. It's a very, I would highly recommend you reading that work. It's this one, I give a reference for it. And then lastly, I tie this back to FPGAs. Remember that slide I showed you earlier on? We have the routing grids and those switch matrices. They have these connections between them to connect this wire segments. So this is just a state machine. It's a transition state machine. And there's this work, which I really like also. What they did there is they developed a Markov decision process from that state machine, and they spelled it out in all the gory details with a PDF in there. And then this is like a pictorial representation of it. And they actually took a very interesting problem for FPGAs. It's test coverage. So the routing grid is one of the biggest resource consuming parts of an FPGA. And what they did there is they described this as an MDP, threw up an RL agent on it, and then they came up with a comprehensive framework to do test coverage. And it's actually very competitive. If they compare with the state of the art at the time, the test coverage required much fewer number of test configurations than a typical dynamic programming based approach, which is kind of the state of the art. And this is all with RL because you have this PDF that you describe the transition function, and then it's amazingly worked. Okay, yeah, so this is very interesting, I think, work. Some practical learnings. Let me go through them quickly. Sorry, I think I'm on my time limit. So one thing about deploying MLCAD in the field, what we learn is, I think this is not only me. I think if you talk to a lot of folks in this area, like if you talk to Siddhartha, who was at Synopsys, now it's NVIDIA. The key factor for deployment of a model is inference. It's not training. You can train you can take as much time to train, but when you deploy it, the runtime for the inference model has to be very fast. So we actually spend a lot of time devoted for speeding up inference engine kernels. We don't use the ones in the libraries. We actually implement our own inference kernels. So that's one key thing you have to know. Also, the feature extraction is time consuming. Like I said, for instance, if my feature set requires graph embedding, I need to use some GNN. GNN is not fast today on a million instance netlist. So it'd be really useful if we have a faster version of the GNN, right? You can make good use of it. So like, for instance, for delay estimation or for some kind of incarnations of a model, you cannot use all the tools sets you have in the world on hypergraphs to use for features. You just have to collate the ones that are fast. Okay, and also not all queries are equal. Like for instance, timer queries, they come in small bursts. You're modifying a netlist and timing optimization, and you just want to know the timing in that particular small sub netlist. Versus a congestion map where you're looking at the whole image. And the reason I mention this because if you do a congestion map, you're doing dense arithmetic. You know, it's you get it. It's it's very friendly for caching friendly. While timing queries are sparse queries, they're not cache friendly. So you have to optimize for that. You know, it's more like calling a timer many times, and so there's sparse acceleration versus dense acceleration, and that's something you have to also worry about when you do your inference deployment. Okay, you also have to come up with a life cycle management for the model. When does the accuracy degrade, and how does it detect accuracy degradation? And even without accuracy degradation, you have new information coming, more models that you're throwing on these, more designs you're throwing on these models. How can you incorporate them into your model? A lot of the models that we've developed have been really, I would say, early generation models, like using gradient boosting techniques, RF technique, and just RF and random forest and gradient boosting. These are not very good for transfer learning. So I think while they're very good in modeling nonlinear behavior, I think I see the need that we should move more toward deep learning, because they allow you this feature of transfer knowledge, which is needed for you to update models. It's very useful to do plug and play data harvesting and modular generation in the chain. Like the Open Road project is great, because if you can have stations in the road of the PD physical design flow where you can plug and play models or plug and play harvest data from the flow, that's very useful feature. We have in AMD we have rapid writes, which kind of in that direction. And then just having great models does not mean better quality results. You also have to do parameter optimization and tuning. So the reason I put ML parameter optimization and ML modeling hand in hand, because they really go hand in hand. Our tool chain was optimized for some kind of model. When you have a more accurate model, it may misbehave. So you really have to do that synergistically. And then there's a lot of interesting work, like I mentioned, in L2O. And I would say from an TILOS perspective and the use domains perspective, I think we need to bridge the gap in scaling. The problems that we need to solve now, especially when we are moving L2O to the field, really, how do we scale solving a problem like a router problem or a routing problem or a placement problem? Right now, we can solve them, and we are working with you, our colleagues in academia, on small problems, small snapshots of these. So finding ways to scale it is a very interesting challenge. And then lastly, and also from foundation perspective, I would say working on those kernels like that are in the feature space, like multi-way partitioning, a fast strength exponent calculator, a fast graph neural net calculator. These are really, really useful, because then we can embed them in our feature set. And these actually, working on this will have a very high ROI, I believe, for enabling L2O in the field. So, okay, I'll stop here. Sorry, I went maybe 5 minutes over time. I'm open to questions if you like.
Wow. So there is this phrase, drinking from a fire hose. And I think Ismail has illustrated that or exemplified that. That was great. Thank you, Ismail. Are there any questions from the audience? Please put into chat or just unmute. Well, people are doing that. I mean, for scaling, which you mentioned at the end, I mean, do you look to decomposition because the FPGA is highly structured, or do you look to sparsification of design representations like netlists, or do you look to clustering and contraction as the key lever? Is it all of the above, or do you have any kind of more promising favorites in mind?
And I would say only above. I mean, you're right, spot on. So like, I know TILOS is you are very big on federated learning and optimization. Yeah, we need that. So like, for instance, we for the next generation of devices, they are an order of magnitude bigger than what we have today. And I think the way to solve it really is through partitioning and maybe consensus optimization. That's the approach. And I think that will be a huge enabler for us to go forward for placement. And I think without it, you cannot really do it. Yeah, and I know this is the same story in ASICs. You need this kind of federated optimization in the flow for physical design. And now obviously partitioning is a key parcel for us because we have multi-die, so that's and multi-way partitioning is very important, obviously. And clustering comes into the picture once you talk about federated optimization. We are working on it, yeah, but we need, obviously it's not a solved problem. It's because it's non-convex, right?
Yep.
Ismail, a very nice talk. Well, thank you for the talk. Just wonder, because there are so many information, so much, could we get a copy of the slides?
The video is actually subject to AMD review. And if AMD, as expected, gives approval, then I imagine the slides as well as the video would be shareable. That's my hope. But certainly the video would go up onto our YouTube channel.
Okay, thank you.
Yeah, thank you. Yeah, most likely, yeah, we definitely would love to share it.
Yeah.
I have a question, Andrew. I hope it's okay if I'm from Qualcomm. So one thing, we work very closely, Ismail. I haven't met you, but we work with Xilinx and AMD for a long time. We do, actually, Dr. Kang has helped a lot guiding on the partitioning problems for us. We do a lot of system level prototyping. I see this work happening, which by the way, none of this is really coming to us. We are big customers. I need to go back to my guys and say, hey, what's going on here? There's so many cool things happening. I'm not getting it. Anyway, but I do, from a research wise, I think, like you said, there is partitioning problem, which you're tackling at the SLR level, right? The multi-die partitioning. There is a next level problem that we often see that solves it because we want to be able to do system level design partitioning with the understanding of how things are going to sit within the FPGA. Today, we don't have that ability to iterate at a system level. Xilinx or AMD said, we're not really looking at it, at least from what end customers like us see. I don't see much on the research front also talking about actually looking at it more at a system level partitioning, because we can avoid a lot of problems if I knew that there's going to be, I'm creating a major inter-die SLR partitioning problem, right? We can change things around. Anyway, I just want to throw it out there. I'm very curious to see how we can collaborate a bit more tightly. I've asked this question to the AMD R&D teams. I don't know, maybe through Andrew Kang's group, we can somehow at least participate in the research. We'll see. I'll find out later.
Yeah, thank you, Professor. Thank you, Dr. Naraya. Yeah, I think it's you're right. This is you've touched on a very important. I know, like in emulation and prototyping, that's a key aspect in system level design. We can take it offline, or but maybe Professor Andrew Kang can say it.
No. Well, typically I'm like the go-between. Once people meet the foundations folks who actually have new ideas, like Yusu or Melvin, who are on this call, they actually stop talking to folks like me or CK or David. So I think that would be a logical next step for the problem to be stated in a consumable way for all the foundations researchers who are more than half of the institute, and then take natural courses from there, likely without me or CK or others in the loop. That's kind of my feeling.
Hi, Mark. I see you.
Hey, Ismail. Yeah, a very nice talk. I just want to make a comment on your last bullet, learning 6, right? So graph definitely very important, and media actually have a huge investment in like trying to speed up graph learning on GPU, right? So both these popular graph neural network packages, like such as a DGL and the Python geometrics, we basically like invest a lot of money and resource to make it run faster on GPU. So actually, if you look at the previous GTC keynotes, I think Jensen actually emphasized that there's new support and a new improvement on these graph networks. So just I think millions of nodes kind of graph is not a problem these days on GPU.
That's really great.
Yeah, significant speed up, definitely compared to CPUs. So yeah, could be very useful, I think.
Thank you. Yeah, I'll definitely definitely look into it. And maybe this is also for Dreamplace. I'm sure Professor Pan has already worked with you on that probably. Yeah.
Sure. Yeah. Just graph along. Especially when you actually have lots of compute that requires on each node.
Ismail, yeah, it's really great talk, right? So truly enjoy it.
Thank you. Appreciate it.
A quick question. So when you talk about the emulation, right, you estimate the runtime. So you said it could also help to close the runtime. So basically you will quit, right? If you say, oh, this cannot be done, you will do further partitioning, or you will do some other things to explore some other kind of branch. Is that the way to use that runtime predictor?
We actually, most of them, so I mean, in emulation, timing closure is very easy. I would say for almost all designs close. I mean, because the timing requirements is very, very simple. But some designs, the challenge there really, because it's capacity limited,
right?
So as you know, they overutilize them. It's some of the runtimes can take like half a day, let's say, and we have a budget of, let's say, 5 hours. Let's say, really, when I talk about the runtime, it's mostly, most of them finish. It's just that the budget that we have for the runtime is very limited. And for those long pole designs, some of them you just cannot, but you really will have to have a long pole design because they overcapacitate. So what they do, our customers, they allocate a data farm, a compute farm, especially for those long poles. We kind of classify them as long poles, and only for the long poles they use them.
Okay, so then you offload the job to other things. I see, I got it. Okay.
Yeah, exactly. Because in emulation, it's all about turnaround time quickly. And so if you collate the laggards, it's good that you know them in advance and you can work on the faster ones much quicker. Obviously, for the laggard ones, we are working to speed up. Like I mentioned, one of the things I showed in the slide was the router speed up for emulation. You can tell this is a very key thing for us, that we need to speed up the kernels themselves.
I think there's a comment in the chat window, and also Sid was raising hands earlier, but I don't know whether I still have the question.
Yeah, is it okay to ask a question now?
Yeah, and then Abdul Rahman after that, I think. Well, there's a chat. Go ahead, Sid.
Oh, okay. Thanks, Ismail. I think wonderful talk. I learned so many things. So one comment is, I think when you were describing this learning to optimize, you kind of treated the RL paradigm as well as a paradigm where the objective function itself is learned at the same plane. Do you think in future we could do that, or is a better kind of or a different kind of classification, like similar to the autonomous vehicle world, level 2 optimizer and level 3 optimizer of this learning to optimize framework possible?
So that's a very good question. Let me see if I understand. So, I mean, if the problem is similar task, maybe it's a good thing to learn kind of the geometry of the objective function, right? If maybe, like you said, in Autodesk or self-learning, maybe the problem is you always have the same objective. So I guess it's a good thing for us to have the RL agent learn the geometry of the objective function. Sorry, is that what you meant by that? Yeah. But I think it will happen naturally. I don't think it's not a feature in RL based on what I know, and I think you also know that it's not a feature that we know that the PDF, that there's any knowledge of it. It is something that you learn through doing like A to C or whatever architecture of RL we are using. I think it happens naturally. And if you only feed it the same kind of problem, I would imagine, I don't know, but maybe the answer, yes, maybe it will learn the geometry of that objective function, because that's all it sees for that particular application. Right. Yeah.
Thank you.
Yeah. I don't know if I answered the question.
Thank you. You did. I just wanted to hear your perspective that how you treat these two things differently. But
but you're right, because I'm trying to use that to our advantage. Like, like we have design flows for these different domains, and we know from empirical studies of that survey I mentioned that if you train it on unlike data, it can beat a classic optimization approach and rate of convergence. So I think this is something really for the foundations and the use domains part of TILOS to explore and help us explore. Does it really work this way? It seems like the potential is there. Can I take emulation design flows and put an L2O specifically for them? And what will I gain by that? I think the answer will be yes, but we need to try it.
Thank you. Yeah, thank you.
I think there's a question in the chat window. I don't know whether I can just read it. It's asking that in learning number 6, graph learning still limited with the graph isomorphism problem, and the fact that GNN cannot differentiate all types of graphs yet. Do you see other complementary representation learning models other than GNNs and graphs, or the path forward is to try to work around on these limitations?
Yeah. So if I take one step backwards, thank you, Abdurrahman, for asking the question. I think it's in ASICs and FPGAs, it's not even graphs; it's really hypergraphs. Right, so there's an intermediate representation. We have to go from, as you know, from graphs to hypergraphs to graphs. So if there's a way even to go on the hypergraph and find some properties in there directly rather than GNN, the GNN really is good for the embedding. I want to get an embedding. I'll give you an example. Like I want to find, just for the sake of argument, I want to find from a given node, a source node to a destination node, what is my delay estimation, right? So I can think of that as maybe what's the depth of the path. Maybe I can embed that knowledge. I was thinking maybe I could use a GNN to have an embedding on that node that will give me the level depth of that node on that graph. Now, it's not a graph, it's a hypergraph, right? So if there's a way to get that, I don't know what the answer is for that. But if there's a way to go directly to the hypergraph and have some kind of embedding, it'd be great. Lately I know Professor Khan has been working on spectral methods, right? Maybe we can go back to spectral methods and have that embedding rather than GNN, which is completely valid. What do you gain from there, right? Or maybe a combination of the two. Yeah, but I think one thing is just how to translate from a hypergraph to a graph, and that question to me is still unsettled. And I think you and Professor Andrew Khan and everybody in this audience are the right people to help us answer that question.
I also have a quick question if there's no one. And feel free for people who have to leave, feel free to do so. I have a quick question regarding, this learn to optimize is really interesting. I'm wondering this RL-based method, in your experience, what do you see as some of the main challenges and limitations, other than you mentioned the scaling issue here already? Yeah.
Yeah, so I mean, there are, honestly, I think the field, and maybe because I'm a novice in it, I mean, I'm more of the optimization classical approach. I'm learning my way through it from working with my colleagues. First of all, I think just practical aspects, you know, like what tool sets do I use? Do I use TensorFlow? Do I open OpenGym or PyTorch? Just these things, right? And I'm not talking about theoretical aspects for RL. The architecture of the network, which ones? I think you need to do it several times, kind of get your hands wet to know that, yes, an advantage, actor, critic method, a framework is a good thing to use for our kinds of problems. That knowledge is not encapsulated in a book, really. It's encapsulated in papers. So I find the way to, as a novice researcher in the field myself, I find when I try to come up with an answer to how do I model this problem, there isn't really a good textbook to go and read. Like there isn't a classical optimization book or let's say Boyd's book to go there and here's the recipe in the book, right? There isn't such a thing. It's mostly Google, right? I Google it and find the answer and then read papers. Really, that's what I think. That's the one thing, because it's a new science, at least for me, and maybe for some of us. I think that gap, if somebody can link it up more, I mean, close that the learning gap, it'd be a very good course, I think. Like, you know, this is I mean, maybe in our domain, like this is EDA, this is placement, this is routing, this is graph embedding. What are the tool sets we should use and model them as such? A lot of it is coming from practice, and I know it's a nascent field. Like MLCAD, the workshop is doing a great job there. ICCAD, ISPD, DAC, all these collections of works. It'd be nice if somebody would, I mean, you, Professor Wang, Professor Khan, or Professor Dave Tan, teach a class on how do I map these problems architecturally to such and such. I think that's very useful. And there are, by the way, I only listed a few problems that we are solving. There are so many problems intriguing to me to solve, and not me, but really it's drinking from a fire hose, because there are so many untapped problems in ED and physical design flow that we want to solve. And the synthesis itself, there's a lot of work that needs to be done. Synthesis, for instance, needs to know this synthesized design, when I map it to this kind of logic, will have congestion implications later on. How do I predict from early on that this is going to happen? I know, like back maybe 7 years ago or 8 years ago, Professor Andrew Kahn wrote this very nice work called Probe, where he did it much earlier, like at the layer, at the manufacturing layers, he developed this predictor that says, yeah, if you do the your layer assignments, like if you're a TSMC, this layer assignment is good for this kind of designs, which will create congestion later on or not. What's the width of those layers and such? I think these kinds of works, I mean, there are so many problems like this we have. And I think ML really is the right tool to use. It's how do I map that knowledge into ML formulation? You know, it's a nice problem to have, right? Yeah. Sorry, maybe I diverted from answering your real question. Yeah, but from a theoretical perspective, I'm really a novice. I'm a learner. I mean, I like the work by Professor Malik. I read the work that your TILOS colleagues have done. I'm drinking from your water hose in that respect. I'm not a theoretician at all in that area. But I think the marriage of ML theory and graph theory, really that needs to be bridged together. Because if you look at ML, everything we do in ML, the deep learners, we're sparsifying them in the end. That means we need to embed some more graph theory analysis on them. And graph theory is very key, I think, for us to enable it. And the other thing that's key, sorry, from a practical perspective, TensorFlow and it has this thing called tapes. You can write optimization, right? You can have design your own objective rather than the cooked objectives in TensorFlow, for instance. Like if you have a tape, I can define my own objective and go on and optimize it. What I think is lacking in TensorFlow and the likes, most of them, it's not lacking. I mean, we come from, like I come from an optimization background, from a constrained optimization background. Most of the tool sets they have are unconstrained, right? So I have to I have to map my constraint into an unconstrained formulation through the regularization term. I'd like to see things like augmented, like an exact penalty method there, a constrained optimization method in our tool set of optimization packages and inside TensorFlow or PyTorch or whatever have you. So I think that somebody maybe in TILOS can do that. It's nice to have the constraint optimization tool sets in there, not just the regularization. Regularization is great for classification, those kinds of problems, but there are other problems that we are solving that are not of that ilk. Like for instance, I want some kind of structure on my weights. I want my weight to be blocked, right? I want to have a structure of the weights themselves inside those neural nets. How do I impose that constraint? Not just sparsification. I really want dense blocks in my weight matrices inside these layers, because the dense blocks I can use Siddhartha's NVIDIA. I can use the GPUs on them because they are dense now, not just sparse. So there are these questions. These frameworks that are not available right yet in our tool sets in TensorFlow and PyTorch, which it would be great if somebody in TILOS would start doing them, right, for constraint optimization. So, yeah.
Thank you. Any other questions? All right, so if we don't see other questions, let's thank Dr. Ismail Bustany again for the excellent talk. Really appreciate you give us this presentation. Hopefully we get to share your slide later. I mean, it really contains a lot of very interesting information. Thanks.
Thank you. Thank you so much. Thank you, everyone. Thank you, Mr. Andrew Kang, for inviting me for this talk. Appreciate it.